Okay, so today we're going to start talking about graphing rational functions. And I want to start with just one example. Before we get into the notes, I think day one, we're going to say, how do you actually look at an equation and talk about how numbers work together? Because I think that's important to be able to see kind of how you can just think about graphing, okay? And so, excuse me, if our function is f of x is equal to x squared plus 6x plus, no, not that. Let's do 5x plus 6 over x squared subtract 4. And I'm going to walk you guys through, through some of these steps to say, how could you actually make a table, make a graph, and look at this function? And I think the big thing to know is, it's not just about what works well and what ordered pairs will work in that problem, but it's also what doesn't work. And that will tell us facts about that. If you're walking around your house, you're like, oh, this light switch isn't working. Well, then you're like, that's a problem. That's actually good information to know. And then you can say, well, that helps inform what is going on in your home. Is it just a light bulb? Is the switch broken? Do you need to go downstairs and fix, do the fuse box? So is there a problem with that? But problems can yield information as well that's just as beneficial as positive ordered pairs that you can put on your graph. And so when we go to find the domain, okay, we're going to say, what are those excluded values that you shouldn't plug into your function? And the thing is, you can plug in a lot of values to this function, except you cannot plug in plus or minus 2. Why? Because the denominator is x squared subtract 4, and the two values that make the denominator to become 0 would be the values where x is equal to plus or minus 2. And so you can get that by setting the denominator equal to 0 and solving, and then figuring out what values make it be 0 in the denominator. And so that would be important for you. So those two factors, where those two things occur, are going to be informational pieces. And so step one is to look at the domain. Step two is to say, okay, what am I going to do with those excluded values? And there's two things that could happen. Part one would be, so let's put excluded values. Okay, and so we've got excluded values, excluded values. And so part one would be, if you have excluded value, it could be a whole. How? If there's a common factor on top and bottom. What do you mean? Well, we're going to always factor our function. Why? We can see more details about it. Okay, just like if you have a broken bone, your doctor will put you in front of an X-ray machine and say, let's see what's going on here, an MRI, or who knows what it is, to get more information. And so this is a way to look at your function and say, okay, what is actually going on here? I see x plus 2 and x plus 3. I see x plus 2 and x minus 2 when you factor this. And notice there is a common factor on the top and the bottom, and that common factor is going to be this x plus 2. Okay, and I'm going to highlight this. I'm going to go over here, and I'm going to say, okay, guess what? If you have a common factor on the top and the bottom, it's going to make a whole. Okay, color code your notes. Make sure that's good so that you can see, hey, guess what? If you have a common factor on top and bottom, well, then that means when if x is equal to -2, then we're going to have a whole. Okay, and so that's going to be where one of the problems is. So what you do then is you're going to look for that ordered pair where there's a whole. It literally is a donut you plot on a point. And that, if you looked at your graphing calculator, you'd see error if you plugged in -2. And if you're looking at your graph, you would notice that there's going to be. Sorry, I'm going to fix my colors a second. You would notice that you would have a gap in your graph. Okay, just and then we continue right after -2. And so to figure out what that ordered pair is going to be, you would reduce this. Okay, so you're going to have a third format of this, just like you have multiple pairs of shoes in your closet. and you use whichever pair of shoe is appropriate for the situation, you're going to have 3 different forms in this case, because there is a reducing of this function. And so most of them just have 2 forms, the unfactored and the factored form. But because it simplifies, you're going to have 3. And that's awesome. We like it when there's a whole, because there makes a more easy, item to graph. Okay, so an equation to work with to graph. And so what we want to do here then is you've got to plug your -2 into this most reduced function. If you try plugging it into the top one or the next one, you're going to get a frowny face. You're not going to get an actual answer. But if you plug in -2 into this last function, okay, use this, and you plug in -2, you're going to get -2 plus 3 and put it over -2 minus 2, and you're going to get 1 over -4, so -1/4. And so there's going to be a gap or an open circle at that specific point, okay? And I'll show you what that looks like in the Scotia. The other thing is, if there's another problem point, you're going to have a vertical asymptote. Okay, so vertical asymptote is when the function becomes undefined. Okay, you know a vertical line is that. And what we want to say is, are there other values that aren't wholes that are going to make vertical asymptotes? And if you notice, you see that this other denominator value is going to it doesn't have a top, matching factor on the top. And so this value is going to make it undefined. Okay, you could have more than one vertical asymptote. So in fact, if the x plus 2 didn't have a matching factor on the numerator, you would have 2 vertical asymptotes, one at 2 and one at -2. And now because the second one doesn't have a matching factor on the top, you set it equal to 0 to solve to figure out what the asymptote would be. So the equation of the vertical asymptote is x equals 2. And so, make a quick little sketch. What we'll notice is we have a vertical asymptote at 2, and we have an open circle at -2 on -1/4. Okay, and so your graph probably is going to look like something like this, at that point, and we'll get more details moving forward. But you'll notice there's this open circle there, and then it's going to go towards that asymptote at some point. Now we're going to be moving on and seeing what else can we notice about this graph. Step 3 is let's look for a horizontal asymptote. Okay, so I'm going to go off on a little diatribe because I feel like I can just say, hey, do this and you'll get the answer. But I also feel like I want you to know kind of what you're doing, because I think that makes for, a much deeper understanding, and then also perhaps better retention on what we're actually talking about. So you don't have to know this, but I feel like it helps. And so, feel free to ask me additional questions if you want to on your own time. So let's talk about this. Okay, so now I'm messing up my whole screen. Okay, so what I want to talk about is end behavior. Okay, I'm going to go on an aside so that we can talk about what happens here. When we, in previous chapters, we talked about end behavior, we said, okay, if you've got like y is equal to 5x to the 4th plus 3x plus 1. Okay, and we talked about what is that graph going to look like. We said, oh, that looks like 2 arms up on each side. The biggest degree term is the x to the 4th, and it has a positive coefficient, which means that your graph is going to be doing something like this. Okay, and furthermore, the end behavior is as x goes to infinity, if you put in a big number for x, like 10, and you do 5 times 10 to the 4th, and then you do some more stuff, you're going to get a bigger number. The bigger the number you plug in for x, the bigger the result's going to be. And your graph will go to infinity. The bigger numbers you plug in for x, you're going to get bigger and bigger results for y. Okay, and so if you slapped a negative in front of it, your leading term would be negative, and it's even. So it's going to go to, be both arms down. So why do you talk about that? Well, we kind of disregard the other terms because the highest degree term is the most influential on graphing a function's end behavior. Well, to look at today's functions, we don't have just a single polynomial. We have actually 2. We've got a numerator and a denominator. We want to say, okay, well, what is the end behavior of this graph? And your graph literally could go to infinity. Yes, it could. On the other hand, it may actually have a glass ceiling where you plug in values, and the more you plug in, it's not going to go to infinity. It's going to go to a specific value. And so maybe that glass ceiling, like, is there a limit to how much money you could earn? Or is there, maybe it comes out from the bottom or it comes out from the top, and to say, hey, it's going to get closer and closer to a specific value rather than going to positive or negative infinity. And so you're like, that is weird. Well, let's look at it. What if you had f of x is equal to, I don't know, 10x squared plus 3x plus 1 over, say, 5x squared, plus 7. Well, again, you look at the highest degree terms, and if you plug in a big number for x, you can kind of disregard what's going on with these other two terms here because they're not very influential. The highest degree terms are the most influential when you plug in big numbers to see what is going to happen. So again, we're trying to look at what is that in behavior. And the thing is, say you plug in 100 or 10, okay? So 5 times 10 squared over 10, or below 10 times 10 squared. So like 10 times a big number squared over 5 times that same number squared. Well, if you think about math, 5 times a factor over underneath 10 times the same factor, the factors cancel out, and the answer is going to be reduced to 2. Okay, so if you plug in big numbers, your value is going to get closer and closer to y equals 2. And that means there's a horizontal asymptote at 2, that your graph is rising and rising until getting to 2, but it'll never get higher than that, or it's falling to 2 at some point. So it means that there is going to be, your graph is going to be going to that specific value, not going to infinity. Okay, so the ratio of the highest degree terms. And that will tell you somewhat about the end behavior, something about just saying, where is this graph headed? Okay, so we're going to be talking about what you could notice as you're doing some questions here. And so this is kind of something where you talk about in calculus and stuff, like how do numbers behave in functions? What happens when the numbers get big? What happens when they approach specific values? So we're leaning into that a little bit, but absolutely in further classes, you will learn more things. This is just a dip your toe in the water type thing. So horizontal asymptote would be kind of like a glass ceiling or floor. Okay, and so here are 3 little examples. I'm going to give you A, B, and C, so you can say, okay, if I got this would be the horizontal asymptote, etc. Okay, so if you had something like y is equal to, like we just did, 8x to the third, it doesn't matter, just look for the highest degree term, plus 2x over, let's see, 2x to the third plus 1. Again, you've got to look for the highest degree terms. And you're writing the ratio, you're going to write the ratio of the highest degree terms coefficient. Okay, so let's write this ratio of highest degree terms. Okay, and so I was going to try to get a highlight, but it looks like I'm trying to cross this out. Okay, so you got 8x squared over 2x cubed, or 8x cubed over 2x cubed. So the ratio of those highest degree terms is going to be 8 divided by 2. So the horizontal asymptote would be y is equal to 4. Okay, and so you have to have the highest degree terms and the ratio, and they have to match. Okay, so the second example would be, okay, what if you had y is equal to 3x plus 1, and I intentionally left a gap there, over, say, 8x squared plus 7. Okay, notice the highest degree term is x squared, but you have to have a matching term on the numerator and denominator so you can find that ratio. Well, if you don't have a matching term, you have to create a phantom term. Okay, and so we're going to put on the numerator a 0x squared. Okay, so that it has a teammate, so you can match up the highest degree term. So if I write the ratio of the highest degree terms, you got 0x squared over 8x squared. So 0 divided by 8 is going to be 0. So if you see something like that, your ratio is going to be y is equal to 0. And y equals 0 is just going to be on the x-axis. So there'll be a dashed line on the x-axis. Okay. And this third scenario I'm going to talk about would be, what if you had y is equal to, say, 8x squared plus 7 over, 3x plus 1. Now notice it's missing a teammate on the denominator. And so again, you need a phantom term. So if you put 0x squared on the bottom, okay, now we have a teammate for the highest degree term. Again, they have to have a match set, okay? Ratio of the highest degree terms, they have to match. So 8 divided by 0, what do you think about that? Well, it's undefined, so what's that mean? That means there isn't a horizontal asymptote, okay? No horizontal asymptote, okay? Now, one thing we didn't talk about in class is we will be talking about, is there an oblique or slanted asymptote? Okay, and I'm going to save that for tomorrow. That is if the degree of numerator is 1 higher than denominator. What do you mean? If you had a function where you had x to the 4th plus 5x plus 7, and on the denominator, your highest degree term was x to the 3rd. Okay, it doesn't matter what coefficients are. Well, then what you would do is, and we'll talk about this, is you would divide using synthetic division or long division to see what quotient this function actually approximates, because fractions are running around saying I could divide if I wanted to, but I'm going to wait a little bit. Okay, and so if the degree of your numerator is a little higher than the denominator, then you can actually divide it, and then you'll see, oh, your graph will approximate a slanted line. Okay, and so you would divide it by long division or synthetic division, and to see what shape your graph would go towards slanty wise. And weird thing is that when you divide it, you ignore the remainder, because it's kind of like an ish, like it's kind of like this ish. Okay, kind of. Okay, and so you'll divide it and throw away the remainder, and so you'll get something like y equals 2x plus 3, and you'd graph that slanted line, and your graph will approximate and go towards that slanted line. So we'll talk about that more in class. And then the next thing we're going to speak about would be, and I gotta see if I can scooch up my paper. Yeah, I got this. Would be the intercepts. Okay, and so the intercepts would be the x-intercept and the y-intercept. So if you want to find the x-intercept, the deal is that, if you look at a graph, anything on the x-axis is a number comma 0, okay? And so you let y equal 0. Now, the thing is this, it's kind of weird, with fractions. And if you have never thought about fractions letting y be 0, probably now's a good time to start, okay? And so it's not unlikely that you've never done that. So in our function, if you let y be 0, you'll see x plus 2, and you'll see x plus 3 on the numerator. Use your factored form, okay? Use factored. Okay, and then I should put up here the ratio of the highest degree terms. I would say use original form. Okay, and so our problem that we have is going to be, if you look at the original equation, it's x squared plus 5x plus 6 over x squared minus 4. And so ours is going to be, if you look at the ratio of the highest degree terms, you're going to get y equals 1. So on our graph that we're going to do in a minute, you're going to get y equals 1. Okay, pardon me here. And so the intercepts are going to use the factored form. And so we've got this here. Okay, and so if you're trying to solve it, okay, how do you make a fraction equal to 0? Well, if the numerator is 0, okay, so the numerator is what we're going to set equal to 0 for this thing, okay? Oopsie, we want to highlight. So if the numerator is 0, that's what we're looking for, okay? And so you can make a note. But the thing is this, if you set the top equal to 0, well, then you're going to figure out what values make the whole fraction 0. Okay, and so that's kind of a good concept to think about with number sets. But the problem also is that we already have x plus 2. That is a whole. So something cannot have two jobs. So it can't be a whole and an x-intercept at the same time. Okay, so don't be telling me. They could have, any graph could have a couple of x-intercepts. It could have no x-intercepts, but nothing can have two jobs. And so you set let y equal 0, but you actually are going to say set numerator equal to 0. Okay, so that's what we're going to do. So x plus 3 equals 0, so x is equal to negative 3. So that means your x-intercept is really negative 3 comma 0. Okay, so that's how you find it, is set the numerator equals 0. That's how you make, figure out what x values make the y become 0. Okay, the next thing is we want to find the y-intercept. And to find the y-intercept, we are going to be let x equal 0, and then we're going to use original form. And so on the original form, if you recall, it is y is equal to x squared plus 5x plus 6 over x squared minus 4. Now, when you plug in x is 0, you're going to plug in x is 0 to all the values for x. And so you're going to get 0 squared, which is 0, plus 5 times 0, which is 0, and then plus 6 over a 0 squared subtract 4. So all the terms that have x in it, when you plug in x is 0, will go away. Okay, so that's kind of a cool thing to do. So your answer is actually going to be the ratio of the constants. Okay, so if you plug in x is 0, you're going to get the y value to be 3 over negative 4, which is 3 over negative 2. So your answer is going to be 0 and then negative 3/2. Okay, so that's kind of a good thing to see as well. So we got the x-intercept. Now, an equation may have no y-intercepts or one y-intercept. It won't have two because it's going to be a function. And so, yeah, there we go. And so let's graph everything we know so far. Okay, and so I'm going to erase this. Oh, maybe I won't. Let's just go here. We'll make a new graph. And so we have a an asymptote at y equals 1. We have a vertical asymptote at 2. We have an x-intercept at negative 3, 0. Pardon me. We have a hole at negative 2, negative a fourth. We have a y-intercept at 0, negative 1.5. And so you can see we kind of have these branches, the branch over here that goes towards our two asymptotes. But we really have no data to the right of our vertical asymptote. And you really need to have at least 2 points on each side of a vertical asymptote. And that will help you get a better picture. So the truth is that you, on the top of this, and if I can scroll up, we'll see what happens. We have 3 forms of equations that we could use. Now, if we're going to plug in a huge volume of points into our equation, we can pick any of those 3. We don't always have 3. We only have 3 if one of the factors reduces. But because one of them does, we can use the bottom one, which is the easiest, to be able to plug in our values. Okay, and so I want to pick 2 values to plug in to the right of that vertical asymptote so I can get some data that's bigger than 2. So if I plug in some values to our graph, and I say, okay, well, I'm going to plug in, say, 3 and say 4 to see what happens, I'm going to put them into my easiest function, which is going to be y is equal to x plus 3 over x minus 2. I took that from my third equation. If I plug in 3, I get 6 over 1, which is 6. If I plug in 4, I'm going to get 7 over 2, which is 3.5. And so you can plug in, you can graph these points. 3, 4, 5, 6. Okay, so 3 gives us 6, and 4 gives us a 3.5. 1, 2, 3.5, and we can graph this. And so we're getting some data points, and it's going to go towards those asymptotes because that's what the graph does. And the other thing is, I will on some graphs ask you to use your graphing calculator to do it. And so the way that I would suggest you put your calculator is y is equal to, and I would put the numerator in parentheses, and then I'd use a division sign, and then I put the denominator in parentheses, and then do second table and push graph and look and see what it is. If you use the fraction key, all your answers will be in fractions, and some of them are not loving. They're like 22/7. You're like, I don't know how big that is. So if you do the division key, how you enter it gives the thing, so it'll give you decimals instead of fractions for your answers. So that I found for kids to be like much more easy to find some points to graph that. So this is day one, and in class we did one more question of practice, but on day two we are going to be doing some more practice and talking about the slanted asymptote or the oblique asymptote. All right, thank you so much. Have a good day.